It is difficult to understand just how devastating the Great War was for Europe. It destroyed the illusion of the inevitability of progress and brought to an end the modern era. It brought about the collapse of the remaining autocratic monarchies and ushered in a new dominance of political systems based off the idea that the power of governance rested with the people. More than anything, it left the generation scarred and cynical of the institutions that had been shattered. This could also be said to be true for the work of science as well. After the Great War, physics came to be dominated by big science experiments and the work of the theorists who moved beyond what could easily be seen to those things that were outside of the typical human experience. For a man like Ernest Rutherford, so used to the elegant tabletop experiments done with sealing wax and evacuated glass tubes, it could have also meant the end of a fruitful research career. Many times, as the field progressed, those whose minds were more open and flexible to the vistas the new paradigms opened up left those who had begun the initial researches behind. But such was not the case for Rutherford. As the world changed, so did he, and in doing so, he continued to influence that change profoundly. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series number 2, A History of the Atom. Episode 12.2, Supplemental-Ernest Rutherford, After the Great War. Even before the war had ended, Rutherford had moved back into the laboratory at Manchester. No longer was it a bustling hub of scientific activity. Its halls were mostly empty, as the young men who had filled them had gone off to fight and often die in the conflict that continued to consume Europe. The Cavendish at Cambridge was empty too, much of its lab space being given over to the billeting of officers. Yet there was Rutherford, tinkering with something that had caught his attention just as the war had engulfed them all. Marsden had started the work under Rutherford's supervision. He had been working with bombarding nitrogen gas with alpha particles to see what would happen. However, just before the outbreak of the war, Marsden was selected to be the chair of physics at the University of New Zealand and had left Manchester without finishing the work, intending to pick it up when he got to his new appointment. However, Marsden didn't get to the Antipodes, as he was made an officer in the New Zealand Expeditionary Force and was sent to France. There he would earn a military cross for his service. As Marsden traveled first to New Zealand and then to the trenches of France, Rutherford took another look at his research. What Marsden has observed was that some sort of particle was coming out of the collisions with a very high speed. These H particles, as Marsden called them, would then hit the scintillation screen, causing a bright flash of light. He surmised that what he had discovered was a fourth type of radioactive emission coming from the alpha particle source. Rutherford, however, was not convinced by that explanation. He wrote to Marsden asking if he might continue the experiments, to which Marsden responded in the affirmative. So, while all the world was raging around him, and he was distracted by his work on anti-submarine warfare, Rutherford would retreat from time to time to the lab at Manchester to return to the type of investigation he loved. Over the course of hundreds of experiments, Rutherford became convinced that an entirely different process was taking place than the one Marsden had surmised. What he concluded was that the alpha particle was interacting with the nitrogen atoms and combining to form an atom of oxygen in such a way that a single hydrogen atom was being chipped off in the process. It was this hydrogen atom, ejected at high energy, which was lighting up the scintillation detector. In other words, in 1914, Marsden had actually succeeded in splitting the atom for the first time, only he didn't know it. By 1917, Rutherford was convinced that he did. When Marsden returned in Manchester in 1918, after completing his military service, he intended to collect a few things and then sail for his new position. Rutherford interrupted this line of thought with a, "You'll be staying with us, of course. I want to show you something." Needless to say, Marsden's departure was delayed for a time. Rutherford had modified Marsden's original setup somewhat, replacing the evacuated glass tubes with a small brass cylinder that was less susceptible to radioactive contamination. One end of the cylinder was sealed with silver foil thick enough to stop any alpha particles, but thin enough to allow Marsden's H particles to pass. He then filled the cylinder with a variety of gases, one at a time. While regular air showed a few scintillations, hydrogen, carbon dioxide, water vapor, and oxygen displayed none. However, when he fed pure nitrogen into the cylinder, the scintillation screen lit up brightly. This was clear evidence that the particles were not coming from the radioactive source, but from the interaction of the alpha particles and the nitrogen gas. Rutherford had also determined that the particles were hydrogen nuclei with one positive charge by determining their charge-to-mass ratio using both electric and magnetic fields. The implications of this discovery were profound. The first was that Marsden and Rutherford had succeeded in transmuting one element into another, in this case, nitrogen and helium into oxygen and hydrogen. While not quite what the alchemists of old had had in mind, this was the scientific fulfillment of their goal. The second was that Rutherford now had some sort of insight as to what the nucleus was made of. As you will recall, Rutherford's model of the atom had a small, positively charged nucleus, but what no one knew in 1911 was whether that nucleus had any structure. Rutherford thought that it did, but there were many who were of the opinion that it was a single solid mass with a given amount of charge, much like a tiny version of what Nagaoka had surmised with his Saturnian model. Now, since the alpha particle was a helium nucleus and the target was a nitrogen nucleus, the hydrogen nucleus had to come from somewhere. Since it only had a charge of +1, Rutherford correctly surmised that it was a basic building block of every nucleus. Combining these discoveries with the work of Moseley, Rutherford concluded that the nucleus of the atom was made up of a certain number of single positive charges. If the element was hydrogen, there was one of these. If the element was helium, there were 2 of them. If the element were iron, there were 26 of them. This, of course, was a resurrection of Prout's hypothesis. Going back to our episode on the periodic atom, you'll remember that Prout had suggested that all elements were made of combinations of a single particle he called a protyle. This hypothesis had foundered on the evidence that things like chlorine didn't have an atomic weight that was an integer multiple of hydrogen. It was 35.5 rather than 35 or 36. So why didn't Rutherford's reworking of Prout's hypothesis suffer from the same problem? The answer to that question takes us back a few years and the work of Rutherford's old collaborator, Soddy. Building on the work of Swedish chemists Daniel Strandholm and Theodor Svenberg, who were able to show that the decay products of several radioactive elements seemed to occupy the same places on Mendeleev's periodic table, Soddy coined the term isotopy from the Greek words meaning same place. In 1907, chemists Herbert McCoy and William Ross showed that thorium and radiothorium were chemically identical in terms of their reaction with other elements. Bertram Boltwood at Yale found similar results. In 1911, Soddy wrote, quote, "The conclusion is scarcely to be resisted that we have in these examples no mere chemical analogues, but chemical identities. Chemical homogeneity is no longer a guarantee that any supposed element is not a mixture of several different atomic weights, or that any atomic weight is not merely a mean number. The constancy of atomic weight, whatever the source of the material, is not a complete proof of homogeneity." In other words, what Soddy was saying was that while chlorine had an atomic weight of 35.5, that measurement might not mean that each atom had that atomic weight. What might be the case was that half of the atoms in chlorine had an atomic weight of 35, and the other half had an atomic weight of 36. Soddy used the term isotope for the first time in a paper in 1913 to describe an element that might be found in two or more types with different atomic weights but that were chemically identical. The Harvard chemist Theodore W. Richards confirmed this idea in 1914 by studying lead. By this time, it was known that lead was the end product of several radioactive decay processes. In other words, one could start with a number of different types of radioactive elements, and by allowing them to undergo their natural radioactive decay processes, the end result would be the element lead. Soddy and another student of Rutherford's, a guy by the name of Fangens, had shown how each of these decay chains, as they were called, could result in lead with different atomic weights. They had then gone on to show that the three types that they were working with were actually chemically identical. Working with a German student by the name of Max Limbert, Richards was able to show that the atomic weight of each of these three species of leads was different, thereby confirming Soddy's idea of different isotopes of the same element. In 1919, Rutherford published a series of 4 papers in Philosophical Magazine titled Collisions of Alpha Particles with Light Atom. In one of the papers he writes, quote, "From the results so far obtained, it is difficult to avoid the conclusion that the long-range atoms arising from collision of alpha particles with nitrogen are not nitrogen atoms, but are probably atoms of hydrogen. If this be the case, we must conclude that the nitrogen atom is disintegrated under the intense forces developed in close collision with a swift alpha particle, and that the hydrogen atom, which is liberated, formed a constituent part of the nitrogen atom." Now, 1919 was also a monumentous year for Rutherford in another way. In March of that year, J.J. Thomson was made master of Trinity College at Cambridge, and a replacement was needed to lead the Cavendish lab. The lab was in a bad spot. The war had stripped the lab of both men and materials, and at age 61, it seemed like Thomson would lack the energy needed to restore it in this time of meager resources. While there was a good bit of negotiating to be done, both to protect Thomson's prestige and to adequately compensate Rutherford for his new position, Ernest agreed to take the post, and thus returned after 20 years of wandering and remaking physics. As he had done at McGill and Manchester, Rutherford began assembling a team of gifted researchers and clearing space for them to work. One change was that he did less of the research himself now. As his prestige has increased, so had the request to give lectures, serve on various committees, and sponsor or take on a number of tasks. While he was, at times, frustrated by the seemingly endless distractions, he also enjoyed the influence his work on these non-research-oriented efforts brought. In time, this influence would be of enormous consequence. Rutherford brought the lab roaring back by attracting more than 600 researchers, many of whom were veterans of the war hoping to get back to their lives. The group included a large number of Americans and, a rarity for the time, a number of women who Rutherford welcomed with open arms, saying that, quote, "The university is intended to fit the rising generation to take its proper place in the outside world, where, to an ever-increasing extent, men and women are being called upon to work harmoniously side by side in every department of human affairs. For this reason, no less than those of elementary justice and of expediency, we should consider that women be admitted to degrees and to representation in our university." Unquote. Rutherford urged his teams forward, goading them to produce results. He was not, however, a harsh taskmaster. Just as he pushed his researchers, he created a sense of community and belonging. When Marcus Oliphant arrived at the Cavendish from Australia and was greeted by Rutherford, he recalled that Rutherford, quote, "reminded me forcibly of the keeper of the general store and post office in a little village behind Adelaide. Rutherford made me feel welcome and at ease at once." Unquote. He met with his crew for afternoon tea, listening to their work and offering suggestions. On Sundays, he invited the senior faculty and researchers, along with promising students, to his home for longer discussions and conversations. He was also frugal as a director, at least to a point. He believed that a lack of resources usually spurred innovation, a sentiment he often expressed in the statement, "We don't have money, boys, so we have to think." When the war had ended, James Chadwick had returned from Germany, a shadow of the man who had left. He was malnourished, without funds or prospects. Rutherford took him in on Christmas of 1918, just a month after the conclusion of the war, and found him a job as a part-time instructor in Manchester. When he moved to the Cavendish, Rutherford took Chadwick with him and made him assistant director of the lab. Chadwick, in his memoirs, wrote of Rutherford's frugality as director of the Cavendish in this way, quote, "I believe he was essentially a very modest man. I think he was always surprised by what he had done. During one of our talks, he said suddenly, I say suddenly because it had very little connection with our talk on writing papers for publication. You know, Chadwick, I sometimes look back on what I have done, and I wonder how on earth I managed to do it all. I knew him fairly well, because it wasn't only in the laboratory that I knew him. I knew him at home. I knew him in the off-guarded moments when he was not being the great physicist. That, I think, was modesty. It was also a reluctance to be responsible to somebody outside the laboratory. He did not feel he could justify spending so much money on himself and his research students. And this in spite of his unique position in the scientific world, his extraordinary achievements in the past." Unquote. In 1920, Rutherford was asked to give a second Beckerian lecture to the Royal Society. In it, he would dub the H particle the proton, naming it after Prout, who had the idea of a single constituent building block. Additionally, in the same speech, he postulated that there must be a yet undiscovered particle that was electrically neutral that would help stabilize the nucleus and account for isotopy by being present in different numbers. In his words, quote, "It may be possible for an electron to combine much more closely with the hydrogen nucleus, forming a kind of neutral doublet. Such an item would have very novel properties. Its external field would be practically zero, except very close to the nucleus. And in consequence, it should be able to move very freely through matter. Its presence would be difficult to detect by spectroscope, and it may be impossible to contain in a sealed container. On the other hand, it should enter readily into the structure of atoms, and may either unite with the nucleus or be disintegrated by its intense field, resulting possibly in the escape of a charged hydrogen atom or an electron or both." Unquote. The evidence for this idea was thought to be beta particles that were known to become from the nucleus. If there were electrons tightly bound with the protons as part of the nucleus, a collision of sufficient energy could jar one of those electrons loose. Another possible source could be if these doublet particles, as Rutherford called them, were unstable on their own and could decay by releasing the electron during regular radioactive emission. Rutherford named the doublet particle the neutron. While this idea was compelling, it was not without its problems. As quantum mechanics developed the uncertainty principle, it became clear that such a double particle arrangement would have difficulty being energetically stable in any configuration. By 1930, there had been a number of objections to the model that had been raised, but there wasn't a good alternative being proposed, so, as often was the case, the model was allowed to stand. While the 1920 Beckerian lecture was largely ignored outside the physics community, it set off a race to discover the elusive electron. James Chadwick set it as his task to discover the particle at the Cavendish. True to Rutherford's insight, it proved to be a difficult task, and Chadwick would spend over a decade chasing it down. There were a lot of dead ends and wild rabbit searches in the research, several of which, by the way, were initiated by Rutherford himself, who believed that each of the subatomic particles might harbor further atomic-like structure. In 1931, though, Chadwick read of odd results coming out of experiments in Paris and in Germany. In Gießen, Germany, Walther Botha and Hermann Becker found that if the very energetic alpha particles fell on certain light elements, specifically beryllium, boron, or lithium, a form of radiation was produced that could penetrate more than an inch of lead, something that alpha and beta particles just couldn't do. In fact, the radiation was more penetrating than even the gamma rays that were known, and the details of the experimental results were really difficult to interpret. In Paris the following year, Marie Curie's daughter and son-in-law, Irene and Frederick Joliot-Curie, showed that if this unknown radiation fell on paraffin wax or any other hydrogen-containing compound, it ejected protons of very high energy. While not completely inconsistent with gamma radiation, the gamma explanation just didn't seem very convincing. Chadwick, on the basis of his long work, thought he saw evidence of the neutron in the data, so he recreated the experiments of both groups. In 1932, he did a series of experiments that showed that the radiation couldn't be gamma rays. By being more careful with his data taking, he was able to show how a neutral particle with the same mass as a proton could knock hydrogen atoms out of the paraffin with roughly the same amount of energy as the neutral particle would have entered the material with. This, combined with the demonstrated penetrating power of the new particle, was explainable in only one way: a neutral particle, something very similar to Rutherford's neutron, except that it wasn't a proton-electron pair, as the professor had described, but a single particle. For this work, Chadwick would be awarded the Nobel Prize in Physics in 1935. When Frederick Joliot-Curie was asked how he and Irene had gotten so close and yet missed what Chadwick had seen, he is said to have replied, quote, "The word neutron had been used by the genius Rutherford in 1923 at a conference to denote a hypothetical neutral particle which, together with protons, made up the nucleus. This hypothesis has escaped the attention of most physicists, including ourselves. But it was still present at Cavendish, where Chadwick worked. Old laboratories with long traditions always have hidden riches. Ideas expressed in days gone by our teachers, living or dead, taken up a score of times and then forgotten, consciously or unconsciously penetrate the thought of those who work in those old laboratories, and from time to time they bear fruit. That is discovery." Unquote. You can imagine how such a thing might have happened. In order to make scintillation detectors, an observer has to sit in a dark room and let their eyes grow more sensitive so as to see the brief flashes of light once the experiment starts to be run. This could take as long as half an hour, and so you can kind of see Rutherford and Chadwick sitting in this room, passing thoughts, sharing stories. And I'm sure that during that time, Rutherford regaled Chadwick on more than one occasion with this neutron hypothesis he had, and how it might work, and what sorts of things they might expect to see. It was during these darkroom chats, I think, that Chadwick says he became convinced that the neutron was actually a thing. Now, of course, the discovery of the neutron also settles the question of Soddy's isotopes. A new model of the nucleus was developed, with the nucleus of the atom being made up of a certain number of protons, which determined its atomic number, and thus its position on the periodic table, and then a certain number of neutrons that, when added to the number of protons, made up the atom's atomic weight. Using our chlorine example from before, all chlorine atoms have 17 protons. That's what makes the atoms chlorine. However, about half of the chlorine atoms will have 18 neutrons in the nucleus, while the other half will have 19 neutrons. These two isotopes, when averaged together in their proper percentages, give an average atomic weight of about 35.5, which of course is what threw Prout off. During this time between the transmuting of nitrogen and the discovery of the neutron, Rutherford's scientific output diminished pretty sharply. While one might see this as evidence of declining ability, nothing could be further from the truth. The drop in productivity in scientific investigation was more due to the changing nature of his role in the broader scientific community. As Nobel Prize laureate and director of the Cavendish Lab, Rutherford was a much sought-after speaker. Every year he was asked to give dozens of lectures and receive awards. While he turned a majority of these down, he would sometimes be away from the Cavendish for 6-month intervals on tours to promote scientific research and funding. Another enormous demand on his energies was his work in helping rebuild the great scientific institutions of Europe after the end of the Great War. He raised money to restock the libraries of the universities of Belgium that had been destroyed by the German invasion of the country. Additionally, he convinced the British government to pay the Austrians for the radium they had supplied to various British institutions as a way to reopen and refund the Vienna Institute, which was, at the time of this work, still considered an enemy institution. The final thing that pulled Rutherford away from his scientific research was being elected as both the president of the Royal Society and the British Association for the Advancement of Science. In these roles, he was able to govern the development of British science on a national scale and set something of a research agenda for the entire nation. It was here that Rutherford may have had his own greatest transmutation, changing himself from a person who favored tabletop, wax, and string experimentation to someone who would advocate for a move towards big science. Up until the 1920s, alpha particles from typical radioactive sources had had enough energy to investigate the nucleus of the atom. But as the decade progressed, it became more and more obvious that faster particles that had greater energy would be needed to probe the nucleus in greater detail, especially with regards to the heavier elements. The nitrogen experiments from 1917 to 1920 represented the edge of the envelope of what could be done with the methods Rutherford had pioneered at McGill in the early 1900s. Now, history is full of scientists who, once they have staked their claim in one fashion or in one paradigm, find it impossible to move beyond that and, at best, fade into obscurity and, at worst, become institutional obstacles to further progress by younger and more agile minds. In his role as director of the Cavendish and the president of Britain's two most influential scientific associations, Rutherford could have almost stopped the advance of research in nuclear and atomic physics had he remained wedded to the ideas and methods he had pioneered. Instead, he was convinced by some of the brilliant young researchers in his lab, most notably Leonidovich Kapitsa. Kapitsa was a truly unique and eventually tragic character who, unfortunately, we don't have time to talk about in this podcast. However, it was his unique blend of brilliance and charm that, along with the work of John Cockcroft and Ernest Walton, which is what got Rutherford to commit to a program of big science. In 1927, Rutherford made the decision to pursue at Cavendish the project of building a linear particle accelerator for the first time. This was a profound moment in the history of physics, as it marked the first major institution to commit to a new program of research. Miles of wiring and new advanced detectors were about to replace the sealing wax and scintillation screens at Cavendish. Instead of samples of radium, there would be generators that would produce millions of volts that would create enormous electric and magnetic fields that would accelerate particles to speeds formerly unheard of and steer them to target samples for study. These efforts were the first steps towards what we now call the Large Hadron Collider that's run by CERN in Switzerland today, that recently discovered the Higgs boson, and which will restart in just a short time after the release of this podcast for a new round of probing the even more complex mysteries surrounding the nature of matter. In 1927, when Rutherford, Cockcroft, and Walton set out to build Cavendish's linear accelerator, they weren't the only players in the game. By the beginning of the 1930s, there were efforts at the Carnegie Institution in Washington, D.C., in Berkeley, at the University of California under Ernest O. Lawrence with something known as a cyclotron, at Caltech in Pasadena, and in Germany. The race was on not only to chip small particles off a light element, but to truly split the nucleus of a larger and more highly charged atom. Cockcroft had come up with a way, after reading a paper by the Russian theorist George Gamow, to get protons to interact with the nucleus of an atom at lower speeds than previously supposed by using quantum phenomena. This gave the cash and space poor Cavendish a way to move forward without having the resources of the much newer and less restricted American institutions. For a long time, it seemed like the Cavendish team was falling further and further behind the other groups, which regularly announced breakthroughs in producing higher voltages and greater particle speeds. But that wasn't the finish line, and the Cavendish team knew it. There were lots and lots of little issues and problems that had to be solved. Issues like creating and keeping a vacuum strong enough that the accelerated particles would only interact with the sample and not rogue air molecules. And things like dealing with electrical voltages that could easily kill a person who stood in the wrong place in the laboratory. It took Cockcroft and Watson 2 years of hard and sometimes frustrating work to sort through all the issues needed to build a working accelerator. In the end, their setup produced only about 2/3 of the voltage of the American projects to accelerate protons towards a target, but with the cleverness and ingenuity that the Cavendish lab was known for, that was all they needed. In April of 1932, the same year as Chadwick would announce the discovery of the neutron, Walton did the first test runs of the accelerator and got what seemed to be clear detections of having split the atom. What they had done was hit a lithium sample with protons. The proton had been absorbed by the lithium nuclei that had then split into 2 helium nuclei that flew away the sample in order to be detected. Additionally, it was determined that the mass of the end products of the nuclear reaction had slightly less mass than the initial proton and lithium nucleus did. This mass had been transformed into energy, just as Einstein's famous relationship had predicted. This was the first experimental proof of the 1905 special theory of relativity's mass-energy equivalence. The Cavendish team had beat the American groups. As Freeman Dyson would write, quote, "The Americans had better machines, but Rutherford had a more single-minded concentration on a specific goal. Van de Graaff and Lawrence were the hares. Rutherford was the tortoise. The tortoise won the race." Unquote. The group repeated the process with 15 other elements and found that boron, fluorine, and aluminum disintegrated in the same fashion as lithium had. So did uranium. 1932 is known as the miracle year in physics. Chadwick discovered the neutron, Cockcroft and Watson split the atom, and Carl Anderson first observed antimatter, something that had been theorized by Paul Dirac while working at the Cavendish in 1928. It was Rutherford, working at his highest ability, both as a scientist and an administrator, who had made all of these discoveries possible. However, 1932 is known for another, much more sinister reason. As financial disaster began to grip the United States and Europe, the democratic government of Germany proved unable to cope with the economic catastrophe that engulfed the country. One of the solutions offered to deal with this was a return to totalitarianism, and in July of that year, the National Socialist Party, or the Nazis, won 37% of the vote for Germany's parliamentary body, the Reichstag. Their leader, one Adolf Hitler, was swept into power and in 1933 became chancellor. Within months of his election, the first of the anti-Semitic laws were passed, barring anyone who was classified as non-Aryan from holding a post at a German university. Anyone with a single Jewish grandparent was dismissed and left without a means of economic support in a tremendously difficult time. Included in this list were figures like James Franck, Max Born, Lee Meitner, Fritz Haber, and of course, Albert Einstein. Similar laws were passed in Italy, leading to the dismissal of Enrico Fermi, whose wife was Jewish. In May of 1933, 1,500 non-Aryan scientists had lost their jobs in Germany, including a quarter of the country's physicists. William Beveridge, who directed London School of Economics, formed a network to help these individuals immigrate from Germany and find positions at other institutions. The network, called the Academic Assistance Council, needed both money and political clout, and Beveridge approached Rutherford for help. Made the Baron of Nelson just a year earlier, Rutherford agreed to become president of the council and threw himself into it with his customary vigor. He raised money and made the necessary political and academic connections needed to bring both high and low-profile individuals first for tours and then for permanent visas. By 1936, the Council had helped 1,300 scholars find positions either in England or in the United States at a time when there were strong anti-Semitic movements in both countries, and the economic picture was bleak at best. In response to an article that he had written to the Times of London, Chaim Weizmann wrote Rutherford to say, quote, "You have my profound admiration and gratitude. Jews outside Germany have avoided expressing their feelings of indignation in case it upsets those whom, for the sake of peace, are trying to negotiate with the Germans. Your voice, raised yesterday with so much dignity and restraint, brought, I am sure, comfort and solace to many sufferers, and you have placed us under a great debt of gratitude." Unquote. As his work with the Council took up more and more of his time, Rutherford's scientific work slowly came to an end. Nevertheless, he was still a powerful inspiration at the Cavendish, often taking time to pull up a stool with a young researcher to talk and ask questions. Samuel Devens, who was an undergraduate student at the lab in the 1930s, wrote, quote, "The Cavendish was Rutherford's domain. His influence there seemed a wholly natural phenomenon. Benevolent guidance, leadership, and intellectual authority flowed from him, and loyalty was returned. No one would more question his influence on those around him than one would that of the sun on the satellite planets. Rutherford, the Cavendish professor, was the center of light and warmth and light. It was the natural order of things. Young graduates were way out on the periphery of this constellation, but we would bask in the sunlight all the same." Unquote. I wish I had more time to talk about the life of Rutherford. There's so much that could be discussed, including his on-again, off-again flirtation with using nuclear degradation, as he called it, to produce energy. He saw that it could be both a boon and a curse for civilization, something that would be followed up by Enrico Fermi and the Manhattan Project of just a few years after his death. The end came unexpectedly for Rutherford. On October 13th of 1937, he was trimming the trees in the garden when he fell from a low branch. In the fall, he aggravated an old hernia. An operation to repair the damage was successful, but Rutherford's constitution was not up to the task of restarting the process of normal digestion. The professor died on October 19th, which was a sunny, tranquil day at the Cavendish. The scientific community was stunned that such a man had been taken from them so suddenly. His ashes were buried in Westminster Abbey. Chadwick wrote the obituary that appeared in Nature. Quote, "He had, of course, a volcanic energy and an intense enthusiasm, his most obvious characteristic, and an immense capacity for work. A clever man with these advantages can produce notable work, but he would not be a Rutherford. Rutherford had no cleverness, just greatness. The world mourns the death of the great scientist, but we have lost our friend, our counselor, our staff, our leader." Unquote. With his passing, the world was changing too. Scientists were fleeing the old universities of Europe to go to the Americas. In 1938, Rutherford's one-time student, Otto Hahn, managed, along with Lise Meitner and Otto Frisch, to initiate nuclear fission of uranium-238 while they were in exile in Sweden. Before long, there would be the secret effort in the New Mexico desert to beat the German scientific group in developing a weapon based on that technology. Many of the workers there would be able to trace their scientific lineage back to Rutherford, not the least of whom was Niels Bohr, who was known only as Mr. Baker when he visited the project to consult. It is not an exaggeration that we live today in a world of Rutherford's discovering. For those of my age and older, the Cold War and the threat of mutually assured destruction was a product of Rutherford's research, as was the promise of atomic energy. His work, along with that of Marie Curie, has profoundly influenced medicine and the treatment of cancer through both radiation therapies and the development of many of the technologies used today in imaging and diagnosis. He wasn't working towards those goals, but rather merely to better understand the atom. Before Rutherford, the atom was a hard, indivisible sphere that wasn't well understood beyond some chemical properties. After his work, and that of many, many students, humankind understood it well enough to take it apart and put it back together again. Not a bad legacy for a man who, as a child, was known for doing just that to the various gadgets around his mother's home on South Island in New Zealand. Before I go, I'd like to thank everyone for subscribing to the podcast. If this is the Odyssey, then you're the crew. While I might be navigating from point to point, it's your support that keeps the ship afloat. If you have a minute, drop me a note, let me know what you think, and if there's anything you want me to look at. Leave a review so we can reach a few more folks and see if they'd like to come aboard. In the next episode, we'll return to the narrative of the development of humanity's understanding of the atom when we consider the quantum atom. Until then, full sails on you.